Morning, everyone. Hopefully the sound is okay. I do not know. Actually, well, I could probably find out, but hopefully the sound is okay. Somebody tell me if it's not. So today I'm going to be talking about balancing a stick. And if you look under here, I've got an example that I wrote about 20 years ago. And alright, so what we got here is the little black thing here is a small robot which is accelerating or decelerating in order to balance the stick that's on top of it. Now the stick is basically just, it's following very simple gravity law. It just falls down, and it doesn't even use proper physics anyway, but it's simple enough that that we can build something from it. Is my printer working? Kalon, this is not about 3D printing. I'm talking about balancing a stick. Jesus. Alright, anyway. So, in order to rebuild this, I'm going to rebuild this from scratch. I'm not going to rebuild everything though, because, you know, so far in the last few classes we've rebuilt all the graphics. I'm going to use another physics script, a physics library called matter.js. Okay, to rebuild this. So let's start with that. What is this? Paul knows that I am in the middle of this. Or hold a moment there. Oh, it's a different... Jesus. Hold a moment. Right, anyway, so demo.verons.com/balancer2020. Okay, so we've got an empty directory. We're going to start from that. Hello, and hello. Oh, okay, cool. Yes. All right, let's get on with this. So we've got a directory called balancer2020. And we're going to use a library called matter.js. So I'll load that up just so we can see what exactly this matter.js is. It's a 2D rigid body engine, physics engine. Now, by rigid body, what that means is that we can do things like connect things to each other. That's a lot of demos. All right. Anyway. So I'm going to grab the JavaScript. Now I already actually have the JavaScript somewhere else. I'm just going to copy the script from balancing matter.js to here. Yep, clear that. And then there are two libraries I also need from that. So that's balancing libs. Right. Okay, so I've got two directories in here called matter.js and lib. Now, so we need to create, first off, we need to create some HTML that's going to hold the website, web page, and its contents. So I'm going to call that stick.html. Now, if you look at the address that I have here, demo.verons.com/balancer-2020, then you can follow along. You know, you can actually look in that right now, and you can see what I've just put in there. So I'm creating a file there called stick.html, which is going to contain the HTML that I'm doing. So I'll just make that bigger because some people just cannot seem to read what I'm writing. Okay. Now script source equals. So we need to load in the various scripts. So I've got matter.js, and what's the file called? It'll be in build. Unloading the minified version of it. There we go. And we also need to load the helper libraries. Now, it's not obvious that you have to do this, but if you don't load these then some things will break. lib/decomp.js source equals lib/. So what we're building in the first place is just without the intelligence. We're building, first off, we want a stick that's going to fall down, which is it sounds simple. It's actually harder than it sounds. Body slash, and close that. So that should give us an empty page called stick.html. We look in that and it's blank. Okay, now to make it do something, we need to have another script which manages what's going on. Oh, I've got delay down to about 11 seconds, so if you have any questions, ask away and I should be able to respond, you know, pretty quickly. Right, script source equals stick.js. So all of the code we're going to stick into a file called stick.js. Who have we got online? Have we got like just three people? Sorry. Gangster JF. Is it just me? Alright. 6 people watching. Right, so stick.js. Now, so let's open that. Stick.js. And I'm going to create a function there called initialize. And we want that when the page loads, it's going to, when we have this blank page in front of us, that one there, then it's going to call this function initialize, which will then do all the magic and make things happen. Alright, so first off, I'm just going to make it just say hello. Now we'll see that if I load up the web inspector using F12 and look in the console, then nothing happens. It doesn't do anything because we didn't actually tell it to do anything yet. So stick.html, we need to say that when onload equals initialize. So when the body is loaded, it's going to call initialize. Now if we load, it says hello. Alright, so now we can start building. No, I'm here too. Hello everyone. Well, it says there are 6. Yeah, I wonder, I don't know how the numbers work on this. Is that 6 people, or do I count as a person? Because I'm viewing it as well, or does the broadcasting thing count as a person? I don't know. Maybe I'll start one and keep it hidden and see what happens. Right, so now we need to start up the stick.js. Just a moment there. I did an example earlier on. I spent a couple of hours just playing with this library because I've never used it before. So, you know, I did technically what your teachers are doing at school. I learned the subject before the class. Don't know what I'm doing. This is going to be fun. Okay. So with matter.js, it's basically a library which contains a load of different modules. I will be alive watching measurement guy. Thank you. You just tell me whenever there are 8 watching now. Whenever there's 9, you just keep counting. It's everyone that's viewing it, including yourself. Okay. So we need to start off by creating some variables. Now matter.js has a number of different things inside it. So we have the matter engine, which is the thing that makes the physics happen. Then we have the matter renderer, which draws what's in the engine. And in fact, I don't even need to do all this. I don't need to do this. It's just a way of making things shorter in the long term. Let's just start off by creating the engine. So engine equals engine.create. So what we're doing is we're creating an instance of the engine. A library is literally just a list of instructions on how to do things. It's not the actual thing. So you need to use those instructions to create the actual thing, and that's what we're doing here. So we're basically saying, with these instructions, create a copy, a working copy of the matter.js engine. Okay, and then we need to create the world that the objects are going to be stuck in, and then we're going to create the renderer. So the renderer is what draws everything on the screen. Now with this one we need to give it some options. So we need to say, for example, where it's going to be drawn. Now we're basically going to draw it in the entire window here. So in the entire, it's going to take over the entire window. Well, it'll be drawn in the window. So we're going to say what element is going to use. It's going to use the document body. And what engine is it using? Because we could technically have multiple engines on the same page. Even though there's only one engine here, we still need to say which one it is. And any options. Now, if we go back to this other thing here, you can see it's very wide and not very tall. So I'm going to replicate this. It's going to be kind of wide, but it's not going to be very tall. So I'm just going to say height 200. You can see my fingers are getting a bit icky there as I get older. You know, I try and press one button, I hit 20. Right. Yep, and that looks good. Okay. Actually, just there's a mistake. All right. In JavaScript, if we look at this, in JavaScript we have objects which are denoted by this little symbol here, and inside that you have keys and values. So the key here is on the left of the colon, and the value is on the right. Now you don't technically have to put quotation marks now around the. You can do this if you want. But you don't technically have to. It does make it more readable, but I like keeping things nice and short and compact. Now, alright. So we have the renderer. Now if we just say, let's see, engine.run, engine, then that starts the physics running in this. Now because it's an empty world, the physics is not actually going to run on anything. And if I just render that, then we should technically end up with just a kind of a black background and nothing in it. Let's have a check it out. There's nothing. Engine is not defined. Engine is not defined. Oh, because it's matter.engine run and matter.render run. And that should be matter.engine. Matter is the name of the library that we're using. So we're saying inside the matter library, use the world module, etc. And there we are. So that's our world right now. The world has nothing in it. It's completely blank. In the beginning, there was nothing. That's what this is. That's a nice... There's a lot of creation myths. I like these. Creation myths. According to some guys in the Middle East, in the beginning there was nothing, and then someone from nowhere just said, let there be light, and it just appeared out of nowhere. That's okay. That's one creation myth. In South Africa, there's another group of guys who say in the beginning there was nothing, and then the world was made out of ant poo. Yes, ant poo. Okay? And then the modern creation myth is that in the beginning there was nothing, which exploded. I like that one. You're bad at your job, you're fired. Yes. Stop. Yeah, count better. All right. So we have an empty world. Let's put stuff in the world. So we need to create some objects. So we create a kind of an empty holder for the objects, And then let's start putting things in there. So we'll say first off, we want the ground. And we'll say to the, oh, well, we don't do it that way. We say objects.ground equals bodies, which is another matter library. So inside matter we have a module called bodies dot rectangle. Now it has a number of parameters. In this case we have 5 parameters. We've got x, y, width, height, and options. So x and y we're going to set as, the x and y are the center of the object. So I'm going to set that as 400 and 190. Now remember I set this as 200 in height, so 190 is, so that's about 400 and 190 is around there. Okay, and then the width is going to be, what did I write down? 800, and the height will be 10. Do I want that? Yeah, okay. And then the final part is some options. So is static. Now, this is a special case. I'm going to put that in there now. It didn't work. It did not work. Oh, because I forgot to add it to the world. You have to add, you create your object, but then you have to add it to the world. So I'll add that. World.add engine.world. Alright, and then we're going to add in the objects.ground. So we're adding the ground to the world. Did that work? World is not defined. I keep forgetting to stick in matter in front of all these things. Matter.world. Yay! Right. Now, the is static is important here, and you'll find out why when I add the second thing. So the second thing I'm going to add is the robot. Alright, so we'll add the robot. Objects.robot. Evan Kenny is quoting The Hitchhiker's Guide to the Galaxy by Douglas Adams. It's a good book. It's a bit weird. Right, I think that he didn't have a plan for it when he started writing that. He just kind of started writing and then just thought, what'll I add next? And kept going until, you know, it was weird. Anyway, objects.robot equals, and again I've written it the wrong way. Let's try this again. Matter.bodies. It's going to be a rectangle. Our robot is a rectangle. And I'm going to place it at the same x. And the y in this case is 180, so it's 10 above the ground. And the width is 40, and the height is 10. And I'm not going to use any options. Now, if I put that in, I need to add it to the world. Yeah, add it to the world, objects.robot. And we'll see what happens. So we've got a robot. Not much of a robot. Let's just empty these. Now, to show you what this static means, I'm going to move this robot up. So instead of starting at 180, that's 180 from the top downwards. I don't know why they're doing it that way, but 180 downwards. So I'm going to change this to 100, and you'll see what happens. Restart. So it falls. So why doesn't the ground fall? And you can't say because it's at the bottom, because that's not actually the answer. Like, there is no bottom in this. It just keeps going down until computer fails. The answer is because is static true means that it is static. It does not move. So it's basically turn off physics for this. There is no physics to it. Now it's hard to see at the speed at which this loads, but when the robot was falling, it actually was accelerating. So it was properly following physics. 42 is the answer to life. Everyone says that. That's actually wrong. You see, if you read the book actually says 42 is the answer to the greatest question. It's not what is the answer to life. It's what is the answer to the greatest question? And the answer is 42. And then the next couple of bucks is, okay, well, what's the greatest question then? Okay. Now, let's add a triangle. No one knows the answer. 42 is the answer to life. Don't question it, just accept it. Yes, I'm heretic. Okay. So now we need a pointy stick. Objects.stick. And in this case, we're going to use vertices. ES dot vertices. How do you write this? It was some strange way. From vertices. Right. Now, so you give it a left, you give it again the x and the y coordinates. So in this case, 400, and I'm going to just stick it up on 40 just so we can see it drop again, because I like seeing things fall. I'm going to put it on 0, why not? And then, now, this doesn't have a width and a height. A rectangle has a width and a height. Vertices don't. Vertices are basically that point, that point, that point, that point, join them all together, make a shape. So you can do any shape out of it if you want. Can't quit the church, start to burn. Alright. Okay, so 400, 0. Now, so the vertices that I chose in this case, you need to give them points. Now, the points are actually relative to kind of the center of... I still have to figure this bit out, but it's kind of the center of the triangle you're doing. I think it's actually the centroid of the thing. It's kind of weird. It doesn't look right, but anyway. Right, so I'm going to say x, y, x, 0, where, no, what am I doing? X minus 5, y minus 60. Remember, it's all kind of down instead of up. So I'm starting on the top left. So the top left is minus 5, and it's going to be minus 60 in y, because x and y are y is upside down for some reason in this. Then the second one is xy, and y again is minus 60. And then the third one is x0, and y is 60. So that makes it a nice pointy triangle. Okay, that should really all be an array. Looks good. Okay, add it to the world. Objects.stick. Right, let's see what that does. And as a stick. Why isn't it falling over? Okay, who knows why it's not falling over? 7, 6, 5, okay. Why isn't this stick falling over? The stick is not falling over because it's perfectly symmetrical. There is no imbalance. It's not left or right in any way. There's no angle to it. Very good, Amit. It's perfectly symmetrical. Now, the objects in this physics engine actually do have mass, which I can show you by changing one little number here. So let's change this minus 5 to a minus 4. So the triangle is going to be a little bit thinner on one side than the other, but that changes the center of mass, so it's no longer over the direct center of the point. So let's have a reload now and see what happens. It drops down and then whoop, falls over. I like that little bounce at the bottom. Let's try that again. Oh, that's so cool. Let's do that again. I want to see. I think I saw the robot itself bounce as well. It did. That's cool. Alright. That's interesting. It's good. So let's just put it back to be symmetrical. Now we know that physics works, but that's kind of what we want here. Alright. Now, so the next part is that we want this to actually move. Now, first off, I'm going to move this so that it's actually, it starts off starts off bouncing on the robot. So I think it's 40 that I had of that. No, maybe it was 90, 40, 90. Yeah, 90. There you go. 90 is actually, there's a slight jump there. Yep. So I'll add it to 95. Yeah. Okay. So that's directly on top of this robot now. It starts off on the robot. Immerticulio. Yeah. Right. So how do we make the robot move? Let's say we want to make the robot move so that the stick falls. Now, first off, this is all very messy. So I'm going to try and neaten it up a bit. So I can use things called folding in Vim. The Vim is the editor I'm using. So if I ZC, that closes that down. And I can probably close it down by, we'll just do that. That gives me these again. Then I can just close that down. We'll do that again here. I'm just making this neater so we can see quickly where everything is in the file. All right, and then there's the engine here. Just close that down as well. All right. So let's say we want the robot to move. So let's see, where did I put that? So I can actually set a velocity on the robot. So let's say I just put it down the bottom here. This might work. Matter dot. Now I have an example from earlier on that I played with, so I'm just kind of playing around with bits and pieces from the example that I did. So matter dot body dot, where did I put that? Set velocity of objects dot robot. Now, one thing I found from this is that you can't just set X or Y. You have to set both at the same time. I'll just show you why. I'll just prove it. Prove it. X. Let's say I do X 1. I'm going to set X to 1. See what happens. Oh, it's gone. And there's no error. It's just gone. But I think it's gone because we didn't set a Y, so it tried to find the Y acceleration or Y velocity, and there wasn't any, so not a number, and that probably caused an internal thing. Is that JavaScript? Yes, that's JavaScript. So yeah, I do most of my coding in JavaScript because it does everything pretty much. It can work on everything. So leader fans apart. Yep. All right. Oh yeah, look what I did. Made the robot move, and let's try that again. So, is it still moving? Let's increase that velocity. Cool. So it looks like it actually just increased just for a second, and then it stopped. But you see, that's like Jenga. It moved so quickly that the stick just fell down straight and balanced. All right, so we have to basically just keep it moving if we want it all to fall down properly. So I'm going to change this back to 1. But we're going to do a loop. Now, in a physics engine, just like in Android, or not Android, Arduino, we have a loop which manages what happens during each step or each second or each instance, whatever you want to call it. Each loop of the event that's going on. Roombas should scream when they hit a wall. Yeah, actually, I saw a video recently where somebody had attached a gun to a Roomba, so anytime it hit something, it shot the thing. That's mad. Do I think JavaScript will replace languages like C++ and Java? No, I do not, and I'll explain why. Right? I saw something recently where JavaScript is a slow language. It's very, very slow because it's an interpreted language. Everything that's in here, all this code is actually kind of read on the fly. So if I, for example, I'll prove it, right? Set timeout. I'm going to create something which happens in 3 seconds. Okay. Now, if I run that, it's going to be perfectly fine for 3 seconds. But then it's going to realize, I don't know what break things is. And then it's going to break. Oops, broke before that. Why did it break before that? Because I wrote my function wrong, that's why. So let's try that again. 1, 2, 3. Undefined reference error, uncut reference error, break things is not defined. Alright, now in compiled languages like C or C++ or Java, that's not going to happen, because every time you write something down, it has to be compiled, and it will be, you know, it needs to be referenced and kind of written in as machine language into whatever it's running in. But in an interpreted language, it can be interpreted on the fly. Now I can prove that as well. I can prove that it's interpreted on the fly by just saying this. Let's say, no, I'm not going to bother. Anyway, you can basically create your own your own lines of code to run on the fly in JavaScript, but you can't really do that in C or C++. Now, why would you use that? C is if you're creating something that needs to be extremely fast. You might use assembly before that. Assembly is incredibly difficult to write a large thing in, but C is if you want to make something that might be substantial in size, but it has to be very, very fast. So, for example, an operating system. With an operating system, all of the basic things like file access or memory management would need to be created in a very fast language. So C is what most operating systems would be written in. C++ is if you're writing a large thing that runs in an operating system, but you need to have things like objects so that it's easy to program with. Now, I don't use really objects. I mean, in a way, these are objects here, but sort of. JavaScript sort of has objects. They're not really objects. But C++ is object-oriented. So you would say, for example, let's say you're creating a Word spreadsheet. Then you might have a spreadsheet object, and the spreadsheet might have an add sheet method. Right? So spreadsheet.addSheet. Whereas in a functional thing, you would actually create functions which do this, but they're not specifically tied to an object, which would be the spreadsheet. Now with Java is what you learn when you don't know about other languages. You know, it's basically what you're taught in college. Why? Because it's a language. It's not better than anything. In fact, I can't think of any languages worse than Java. Java's a bad language, in my opinion. JavaScript. Why would you learn JavaScript? Because it runs everywhere. You can run it in a browser, as we're doing here. You can run it on a server. You can run it on your watch. You can run it on your phone. In fact, the app that I work on every day of my working life is written in JavaScript. And I use JavaScript for the phone, for the app on the phone. I use it for the user interface that you see in front of you, like on a browser. So I use JavaScript for pretty much everything. Now, I wouldn't use JavaScript for something really, really computationally intensive, such as 3D rendering. Why is that ticking? Stop that. I wouldn't use something extremely intensive, like 3D rendering, because you need something a lot faster, like C for that. But if you were forced to do JavaScript for that, there's something else called WebAssembly, which you can use in JavaScript. Anyway, let's get back to this. So we want to have the robot move, but we don't want it to stop after a second. So what we're going to do is in the loop, in the world loop, we're just going to reset the velocity every single second. So we'll create a callback first off. Let's call it loop callback. And then inside that, we're going to stick this. And then we're going to say that every time the world is drawn, which is pretty much 30 times a second, then it's going to run that. Matter.events. Now, anything that happens is an event. So in this case, we're going to trigger that whenever, in the engine, whenever the before update event runs, then it's going to run this loop callback. And I'm actually going to move this run and render right down to the bottom because they really should be last. After all the definitions, that's when you start running things. So we define what the world is and how it works, and then we start running it. So let's have a look and see what it does now. So it should, it doesn't. Matter.events is not a function. Oh, so whenever it does it before update, then it will do this. Oh, there we go, it just continues onwards. There we go, that's what we want. Okay, it fell off the world. Let's make the world smaller so we can see that. That was cool. So instead of 800, let's set this to 700. So now the world is smaller. Whoops, this world is flat. Yeah. Okay. Okay, now another thing. There's friction in this world. I thought Android apps were only written in Java. Didn't know you can use JavaScript. It would have to be run in an offline browser. Aha. Yes. Yes. So Android apps are written in Java, and iOS apps are written in Objective-C. But you can embed a browser within your app. So there's a system called Cordova, and there's a number of offshoots of Cordova. But Cordova lets you basically create an app, which is basically just an embedded browser. So you create your app, and it has an embedded browser, and you can stick a one-page application in that. So it's basically index.html, JavaScript in it, and it runs as if it is one single page. So that means that you can run the same code on your Android as you can run on your iOS in JavaScript. But it also means that you can run your app in your web browser if you want, like in your website. So we actually, in my business, we have an emulator, which is basically a copy of the app, which anyone can just log into. You know, they just click a button and there you go. There's a copy of your app right in front of you. Right. So yeah, it uses. Kay is so bored staying home that he gets enjoyment. I always get enjoyment from things falling off things. Come on, you know me by now. All right. Now, so how do we know that there is friction in this world? Anyone know? All right, give you a chance to answer that. Okay, very quick. We know that friction exists in this world because if friction didn't exist, well then the robot would slide out from underneath that stick, and the stick wouldn't be dragged along with it. The stick would just stay where it is and then fall down. In fact, the stick would fall down and then off to the side because of the angle that it's at. So there is friction in this, but there's not enough. So what we're going to do now is we're going to stick the robot to, well, stick the stick to the robot. You know, because there is resistance. Yes. Well, that's okay. E- yes, yes, that is true. Yes, so the robot has friction against the ground, but I was more thinking about the stick and the robot. But yes, good point. Very good point. If you set the velocity, then it technically should just keep at that velocity if there is no friction. Okay, I wonder if there's air resistance in this. I don't know. Anyway, so let's now we need to take the robot and the stick and have them stick together. So we do that using something called constraints. Right, so now we need to create a constraint. So we'll say objects.constraint equals matter.constraint. Now I'm going to do it simply first and then just explain exactly how we need to change it. So the simple thing to do is just to say body A, which is going to be objects.robot. Actually, we do this. It doesn't matter which order we do this, but I want to say that the stick is stuck to the robot and not the other way around, because that kind of makes sense to me. Body B is the objects.robot. So now we need to add that constraint to the world. If we don't add that, actually just do that. If I don't add the constraint to the world, undefined. Why does everything fail for me? Matter of constraint. Objects.constraint. Can't read property create of undefined at line 29. Matter dot. What is it? Alright, that word must just be something weird for me. Have the robot and stick together. Yes. Alright. Now, so it didn't work. Why? Because we didn't actually add the rule to the world. So we need to add that rule. So objects.constraint with the S. This should work. Let's check it. Yay! Oh, I wonder. Oh, that's cool. So it looks like the constraint itself has some sort of physicality to it as well. Otherwise, I actually expected the robot to kind of loop down and the constraint line to be dangling underneath, and I expected the triangle to just keep it hanging there. Right, so the problem that we have here is that the constraint seems to be coming from the center of mass of the objects. Now it's not from the center of the objects, it's the center of mass. And this is why I was thinking earlier on, see that triangle there? I was thinking earlier on that the x and y coordinates are actually the center of mass of it. And that constraint is actually what gave me the clue. The Roomba revolution is coming. Okay, so what we need to do now is actually move the constraints down to close to each other. So we say that the constraint in A is going to be down near its bottom. Let's do that. Body, is it body A constraint? Can't remember. Point A. X0. This again is relative to the, it's actually relative to the centroid of the object. And Y 80 in this case. So that should be, that is an oops. I forgot my comma. There. Okay. So alright, let's move this up a bit. Okay, so you can see there's about 10 pixels or so of space there. That's what's going on here. Yeah. Alright. So now we need to move point B upwards. Let's say it's minus 10 that I set it to. Yes. Okay. Commas. Whoops. Yeah. Alright, that looks about right. That's cool. You need to program Asimov's laws of robotics. Yeah, there are no humans in this, so it's going to be pretty difficult to do that. Yes, there is a zeroth rule, but anyone know the rules of robotics in Asimov? I don't know if, like, does anyone read these days? Any of you actually read these days? So Isaac Asimov came up with a list of rules, which are very basic laws, and they're actually very, very difficult to write. Yes, well done, Evan. Evan, you're the man. Oh, cool. And I've forgotten, who's that? Andrew, was it? Andrew. Awesome. People read books these days. That's great. Isaac Asimov wrote a load of books, and they're actually pretty simple. They're really simple to read. They're very, very short. But the all the stories are basically written around these rules, but they're also basically ways that the rules can go wrong, if you think about them. Reading Nietzsche at the moment. Don't do that. If you read Nietzsche, oh, you'll kill your soul. The soul you don't have. You'll kill it. Looking into that void. I don't have the time for books anymore. It's such a pity. But I'll tell you, my favourite series of books is actually Raymond E. Feist's Rift War series, which runs on and on and on for about 30 books. It's really, really cool. Fellowship of the Ring. Yes, Lord of the Rings is an awesome series, and it's much, much better than those films. You know, I think when Andrew Jackson was doing the films, he just kind of didn't want to end them, so he just made them longer and longer and longer. Like that travesty that is The Hobbit. That's like, half that stuff is not in the books. Why will it kill my soul? Oh, because Nietzsche is so... he's so pragmatic and realistic and down to earth, and I think he kind of ignores the humanity of existence, the humanity that's needed. Like, you don't have to be better or Ubermensch or Superman or anything like that. There is no reason for somebody to be better than another. Like, you can just enjoy your life, you know? Personally, if we're talking about philosophers, I'm a big fan of Stoicism, where basically, look, enjoy your life. This is what it is, you know? This is what things are. Make the best of what it is. I mean, you can get depressed about it, you can get angry about things, but that doesn't make your life any better. So you might as well just enjoy what you have and be happy with what you have. Try to improve it if you want, but don't be disappointed when things fail. Whereas Nietzsche, I think anything which goes a bit too in-depth into whether something is better or worse than something else, I don't know, it kind of kills what it is. Kills, like, if it's like Terry Pratchett. You guys read Terry Pratchett. There's a thing called I think they call the arbiters of reality. They basically examine things and make sure that things add up. Now, there's a scene in one of the books where the arbiters of reality are basically examining art to find out, is it worth keeping in the universe. So they're trying to break down art into its component atoms to find the element of art. But there is no element of art. Art is not a piece. It's the sum of pieces, and it's beyond the sum of the pieces. It's what you get after you look at something. It's what comes out of what you're looking at. It's a thing which is more than the sum of its parts. You can't examine something so close that you lose track of what it is. It's like looking at a leaf and saying, I'm looking at 1,000 leaves and saying this is a forest. It's not. The forest is not the leaves. The forest is not even the pieces of wood. The forest is the whole thing, the gestalt. Terry Pratchett, wise man. Yeah, anyway, I think he was a bit of a stoic as well. You have to kind of be happy with what you have, and well, content. Maybe not happy. Content with what you have. And maybe it only happens after you've been broken. You are broken down by the world. Anyway, right, so where were we? Yes, right. So we basically have, where's my stuff gone? Where's my robot? Alright, there we are. Robot. Okay. The next part is actually the hard part. So the next part is the hard part. And the hard part is, how do we make the robot know how to keep the stick upright? Right. Now, technically, we as intelligent beings could look at it and we could say that, well, really what you need is that if the center of mass is too far, is over the point, it's to the right of the point, we'll then move further to the right and, you know, keep doing that until it's kind of balanced. That's an intelligent way of doing things. And in fact, there's a name for that kind of artificial intelligence, and it's called expert knowledge. Expert knowledge, yes, Amit, you have it right, and we will get to that. Expert knowledge is where you already know how to solve the problem, and so you write the rules into the system. Now, I don't want to write the rules into the system. I want the system to figure out for itself how to balance. I watch Cold Bullet. Yeah, actually, yeah, I like Cold Bullet. Cold Bullet's he does fantastic videos. Program it to feel pain. Yeah, yes. Have you guys actually? How many of you have actually looked into artificial neurons, which is what we're talking about here? Who's Grenian? Who are you, Grenian? So, all right. I'm going to show you an example. Oh, right, okay. Now, I'll show you an example. This is something I wrote about 20 years ago. So I'm going to restart it from scratch. This is an example that I wrote 20 years ago, and all that it knows is the current velocity of the robot and the angle that the stick is at. That's all that it knows. And then I'm basically punishing it or rewarding it based on how long the stick is not horizontal. So how long does it stay upright? But I also added in a little bit of code, which is, you know, if it goes beyond the screen, well, then it gets punished, or, you know, it's rewarded for it. It's 9 seconds. So how long is it not horizontal, but also how long is it within the screen? That's cool. Alright. Neural networks. I don't understand the ins and outs of it. Nobody does. Nobody does. Okay, so let's talk about how does that work. Alright. So we've got... Now I'm kind of... This is kind of the engine of a neural network. In this case, I have one single neuron in this. Alright. Let's talk about neurons. What a neuron is. Because a neural network is kind of a group of neurons. But in order to balance a stick, you actually only need one single neuron. You don't even need a full network. You just need one neuron. Now, I'm probably not going to get to build the whole thing in this class, but we'll at least get through the basics of what is a neuron, an artificial neuron, and an artificial neural network. Right, so I'm going to just pull in a spreadsheet. So I'll just create a spreadsheet here. Doopy-doo. Don't need that, I'll just use LibreOffice. Whoops, what the hell? LibreOffice. I want to create a spreadsheet. File, new spreadsheet. There we go. Okay. So what is a neural network? Well, if we just talk about what we're doing here with the little robot here, we have a column here. We'll just call this inputs. So we have the velocity of the robot, and we have the angle of the stick. And we'll say the velocity here is 10, 20 watts, who knows. Angle, let's say it's we're talking about, usually when in computers, when you're talking about angles, you talk about radians. So we'll say it's 1.6, which would be slightly like that. I suppose it's a bit like that. Is that about right? No, it's actually more like that. Anyway, doesn't matter. So these are the values. Now we'll say that the neuron itself is over here. Now what does a neuron do? Well, a neuron has these things connecting in, and I've forgotten the names of them. Come on, you guys that are doing the Leaving Cert in biology, what is it called? I can't remember. Axons? Is that what they're called? I think they're called axons. Is it? Lots of pies and yeah, that's right. Yeah, you have to learn to love trigonometry. Love it. So we have values, and then they read into these axons. I think they're called axons. Oh, I need to look it up now. A neuron. Yes, it's called an axon. Okay, it's called an axon. That's good. Right. So, an axon is the main part of the fiber. Synapse. Synapse is where two neurons meet. Yes, synapse. Oh, yes. That's synapses. Right. So, the synapse is the part that reads in the information and also passes out the information to the next neuron along. So, what we're interested in this case is whether to accelerate or decelerate. So, that would be basically a 1 or a minus 1. Let's say 1 is accelerate, minus 1 is decelerate. So on the inputs we have velocity and angle, and on the output we have accelerate, which could be minus 1 or 1, but it's basically just one value. So how does it know whether to do a 1 or a minus 1? Well, a real neuron listens to the information and it gives it a certain weight. So like a certain value could be coming in, and the neuron is thinking, okay, I get what you're saying, it's not very important. And then the thing keeps saying it over and over, and eventually the neuron says, ooh, you got a point, and it just passes a 1 pass onto the accelerator decelerate. Now, simulating that in a computer is kind of difficult, but what we can do is we can do a more dynamic version of that, which is we can say that each value has a certain weight to it. So we'll say the 20 here, the velocity, we'll say it has a weight of 0.3. And we'll say the angle here has a weight of 0.6. And what we do is we actually multiply those values. So we say that is that multiplied by that. And we do the same here. And then in order to decide whether to output a 1 or a minus 1, we add these two values. So we'll say that plus that. And that gives us a value, in this case 6.96. If that's over what's called the threshold value, well then you output a 1. And if it's not over the threshold, then you might output a 0 or a minus 1. Now there are other ways of doing neural networks as well, which will actually give you kind of a grade from 1, 0.9, 0.8, blah blah blah, right down to minus 1. Different ways of doing things. Right, so that way you can say, I'm fairly sure we should be accelerating right now. Okay, 6.9, very nice. Teenagers. Right, so a neural network is basically a way of inputting numbers and outputting numbers. And that's all that happens in here. It's just inputting numbers, outputting numbers. Well, values, but values and numbers, what's the difference? So how the brain works is that, but it's just happening like, I think it's 100 trillion. There's 100 trillion neurons in your brain. I can't remember how many synapses that is, but it's not 100 trillion squared. You might think that every neuron is connected to every other neuron, but that's actually not true. In fact, neurons kind of grouped, they connect onto a number of others, but it's not every one of them. Animals mesmerized. Yes, I watched this for hours. It never gets... I think I've made a mistake somewhere, because ideally what should happen is that should actually just eventually get to a point where it stops and it's just completely vertical and it just... Okay, I have it now. But it doesn't. And I wrote this over 20 years ago. It'd be nice, like, I have been tempted to correct it, like to add bits or so I can nudge it a bit and see what happens. But I don't want to... I don't blame... Accidentally said... What? What's funny? What's funny? Oh, the 6.9. Right. Okay. Alright. Right. So yeah, I could improve this, but I don't really want to, because that's the code I wrote, and I want to leave it like that. You should put some dirt on the floor and train it to... Yeah, it's brushing, really, so dust popping up off the ground. Okay, so a neuron. This is just one neuron doing this. So you can see it's reading in information and it's outputting one value, which is go faster or don't go faster. Go faster or go slower. Or go that direction, go that direction. Alright, so a neural network is a lot more complex. Now, with a neural network, you don't, like, in this case, we can be very, very certain that this is enough. This is enough for you to go by. So you can just say, with this input, with that input, we now know what to do. But with something more complex, like recognizing a letter is... This little maneuver is going to cost us 50 years. Have you seen The Martian? Actually, I just watched that again there yesterday, and I love that. I mean, I read the book, and the book is brilliant. But the film itself is very good. It's not quite as good as the book, but it's still very good. You know, the book is just... It keeps you going with the details. Now, I'm just going to shrink these down a little here. I'm just going to show you something. Alright, so I made a small grid here. Now, I'm just going to show you something here. I'm going to put in numbers. 1. Yeah. Alright, there you go. Right, can anyone see what that is? What is that? Anyone see that? That's the number, that's the letter A. Exactly. That's the letter A. How do we know that that's the letter A? You know, that's basically ones. And you can think of these blanks as zeros. Let's put in zeros here. That's not what I wanted. Yeah. Zero, zero, zero. Now, it gets a bit trickier for us to see this, because we're now no longer just seeing the ones, we're also seeing the zeros. But this is technically still the same thing. Alright? It's still the same thing. It's the letter rocket. Now, how would we make that into a B? Alright, I'm just going to undo what I've just done here, so we can see this a bit easier. So, if I was to make this into a B, then what we could do is that. You could say that as a B. Or maybe to make it more obvious, you could say that's a B. Now, there's not really all that much difference between the B and the A. And technically, we could just change one letter at a time. Do you know what? That's a B, right? What's that? Is that still a B? What's that? Now what is it? That's an or. That's not a B anymore. But is that a B or an or? You could say that it's almost sure, like a 0.9, that that's an or. You could say that's 0.8 that it's a B and 0.8 that it's an or. You know, so technically you can never tell that something is something else. All you can say is you're fairly sure that it's something. You're fairly sure. It's a USB. No, it's not. Looks like some slippers on the ground. Nah, my slippers are on the ground. So that's a B or an or. Who knows? But the point that I'm trying to make here is that there's actually very, very little difference between a B and an or. So how do we tell the difference? And the difference has to do with these multiples here. So when we multiply, we're basically saying that these that the values, the positions of the values, in some cases are very important, and in some cases they're not quite as important. So this one here, for example, that's not very important for us. It's not very important that that is there in order to know this is a B or an or. In fact, you could say that the position of this one is not important either. You could say that that's a B. It is a B. Even though there's no 1 here anymore, it's not really that important because there is a 1 nearby. So how can you tell that there is a 1 nearby? In that case, you can't just have one single neuron where you have a load of inputs reading it in. In that case, you need a series of neurons where, let's say, you've got some neurons which are basically looking at small areas. They might be looking at that area there. They might be looking at that area there and saying, is there a vertical line? A vertical line. Or, because, you know, basically that's a vertical line, and a 1, 1 here is also a vertical line. So you could say that a B is a collection of lines, some of them vertical, some of them horizontal. Who knows? It's one way of doing it. Now, the point of a neural network, the reason that we write them in the first place, is that we don't want to have to write these rules, like if there's a vertical line, if there's a horizontal line. We just want to say, here's a load of letters. Here's a load of pictures of letters, and here are the values that they are equal to. Now figure it out for yourself. And that's how neural networks work. In fact, I did write a demo for that a long time ago as well. I'll just see if I have that here. Dooby-dooby-doo. Picture recognizer? No. Where's my stuff gone? Yeah. Instead of copying, I just want to move it. Move it. Okay. So a long time ago, I also wrote this little letter recognizer. Demo, blah, 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 blah. Letter dot recognizer. Now, let's see if it still works. Whee! Okay, so what's this doing? This is basically finished training. Okay, so you can see the values here, and it's basically saying how certain it is that it's an A or a B or a C or whatever. This is a network where basically you have a load of inputs, you've got a load of hidden neurons which kind of build up their own determination of are they vertical lines or whatever. I don't tell them what to do. And then you've got a load of outputs as well. So the outputs are basically saying, now if we just look at it's just repeating it, okay. If you look at the inputs and outputs here, you can see it's saying that it's fairly certain that they're not these, but they are that. So it's more than 90%, more than 80%, more than 60% certain that it is an or, an S, or a T, or whatever. But it's also more than 90% certain that it's not these other things. Yep. So basically a neural network is never certain of anything. It's kind of sure. All right, that's in this case. Now remember earlier on I said that they can be 1, they can be -1, or we could set up a gradient. Now I use gradients in most cases whenever I'm using a neural network myself. So in this case, it's recognizing the Z as being a Z, but it's also recognizing the Z as not being an A, not being a B, not being a C. You don't tell it why. But if you were to be able to just go in there and change like 1 or 2 of these little dots, then it should be able to just still recognizing a Z. Now I didn't write the code when I was doing that, but it is possible with a neural network to degrade the image and have it still recognize the image. And that's basically what your eyes do. So when you're seeing something, you're not seeing what's there in front of you. An eye is actually not straightforward, like you see something, it goes directly into your brain. It kind of is, but you're seeing something and it goes through a series of neural networks. And it kind of breaks it down into, shades of gray and squares and circles and, bright areas, light areas, and contrast. So for example, with contrast, if you were to think of an inverted image where you got the reverse the whites and blacks in this, it should still recognize it as a Z if it was trained on that. If it was trained to tell the difference. So your eye basically sees exactly the same way as this thing does, where it's taking a load of inputs, which are single values, and it's giving them all different weights. And then it's just kind of summing them up and saying, yes, that's a flower, or that's a guitar, or that's a piece of rope, or that's a light, whatever. And then it just passes back the abstract information about it. So it's not like what you see from the world is not the world. Going back to philosophy again. You see a silhouette of the world. Who was that? Was that... I think that was aristocracies. I don't know. No, it was Plato. So Plato had this idea of the ideal, and he had this idea of the silhouette of the world. Now, the ideal world is what is real. So for example, this is a phone, but it is not the phone. It is not the ideal. Like, what is the ideal of a phone? The ideal is the absolutely perfect example of what a phone is. So this is a phone, but a phone could be square, it could be small, it could be whatever. So the ideal of a phone is actually when you pare it right down to what is a phone. That's your ideal. The silhouette idea is basically what we're seeing. So you see what you think is the world, but it's not the world. You're seeing what your eyes determine the world to be, and it's passing back abstract information to you. And the way Plato described it, before it goes to your brain, the eye decides what to give weights to everything, including grey, The Nokia is the ideal phone. It's indestructible. Yeah. All right. So if we just talk about Plato there with the silhouette idea. Now Plato had this idea that if you had a group of people that were basically seated in a cave, and they'd been in that cave all their lives, and they were basically tied, and they could only see right to the back of the cave. And they could see basically when the sun goes past, they can see the shadows of whatever passes them out of the cave. So they can see their own shadows, and they can see the shadows of anything that gets past. So as far as they're concerned, what they see, because they have never known any different, what they see is what's real. So if they raise their hand, for example, they can see the shadow raising its hand, and they say, well, that's me. That shadow is me. But that shadow is not that person. As a person that is back outside the cave, you're looking in and you're saying, no, actually, no. You're not the shadow. You are the thing in front of the shadow. But you personally don't see you either. For example, you have never seen the back of your head. You might have seen reflections of it, photographs, whatever, but you have not seen the back of your head. You've also never seen your face. You've seen reflections of it. You've never seen your face though. And in fact, you've never seen your hand. What you've seen is what your eye is showing you of your hand, but your eyes might be lying. How do you know that the red that you see is the same red as somebody else? You know? How, like if somebody says, oh, that's a red bike. Is it? Is it really? You never heard your voice. Yep, that's absolutely true. That's even more true. Because you might hear what you think of as other people's voices, but what you hear is actually different from what they hear, because you're hearing it differently. You're hearing it through your jaw. You're hearing it through your jaw, which is actually, you can make a radio which doesn't have a loudspeaker part. All it does is vibrate a metal rod. If you bite the metal rod, you can hear it perfectly clear. Nobody else can hear it. Your hearing is just vibration, but the vibration is then interpreted by your ears and converted into meaning, into abstract meaning. Yes, we are in the Matrix, or the 18th century term would be the brain in the vat. Okay, that as far as you're concerned, the only thing that is Descartes, as far as Descartes, whatever his name was, what did he say? Cogito ergo or sum. I think, therefore I am. Now the reason, why is that important? What you see in front of you might not be real, because you may be a brain in the vat, you may be a robot in the Matrix, you may be plugged into a machine. Vsauce Michael here, that's what it looks like. Yeah, pretty much. Hold on a moment. Are you real? Yeah. So you might not be real. What you think of as you might not be you. What you think of other people might not be other people. They're just actors, and in fact, that is the philosophical term for other people. They're actors in your world. Okay. Okay, they're actors in your world, but the same. Going back to the artificial networks, the meaning that's derived from the inputs is not the inputs itself. It's just an abstracted version of it, and it's kind of pared down as well. So when you're looking at, it's very difficult for a person to think of two things at the same time. A computer can't do it either, really. Truman Show, yes, you don't know. A computer, you can't think of two things at the same time, and neither can a computer. Instead, what happens is you trust sub-networks or sub-managers in your brain to handle those parts. So when you're walking along and reading at the same time, part of your brain is walking and part of you is reading. And if you think of it further, that the part of you that's walking is not even controlling the walking. Because what is walking? Walking is a series of controlled movements of muscles. You don't actively think about every single muscle that you want to move. You just basically, you say, I want to go over here. And then you trust that part of your brain knows how to do that. So the way I think of this is that the you that you think of as you is actually a manager in your brain. You are, the conscious you is managing other parts of you, which are also entities. They are also kind of people, and they're in your brain, and they're also you, but they are workers. They're basically, you're saying, I want to go over here, or I want to read that book, but you don't have to control it. You don't micromanage it. You don't like read a book and read the word and extract the meaning. You just extract the meaning. You're saying, read the book. Okay, now I know what it means. You might not even have noticed you reading the words. When you're reading a book, for example, no. No, I know I go on about philosophy, but that's it's all fascinating. I love that stuff. All right, so when you're looking at a book, you are not actively reading every word and parsing the meaning of a sentence. Instead, you are trusting that the part of you that has learned how to read is going to do it for you. You kind of take a step back. After you learn how to do something, you step back and you trust that part to do its job and come back to you with what it finds out. And I believe that that is how learning works. You know, so when you're learning to juggle, or if you're learning to ride a bike, the first thing you do is you do actually learn how to do it. Tiny little bit at a time. You learn how to move, what the pedals do, what the handlebars do. You learn when you're juggling, like, what are you actually doing? You learn that it's all about the throw, it's not about the catch. But you have to figure it out for yourself. But then after a while, you don't have to do that anymore, because you trust that the part of your brain that you're teaching to juggle, which is not you, it's part of your brain. You're teaching a sub part of your brain how to juggle. And then you step back and you say, okay, juggle for me. And your brain is just doing it, and it can do it. And then you just take the applause. Now, where does that go from neural networks? How does that work? Well, with a neural network, if you look at the letters there in front of you, the first thing it does is it takes a very long time to examine every single black or white pixel and to extract meaning from it and say, that's an A, that's a B, that's a C. And it uses punishment and reward in order to train this. So it would basically go through it and say that, like, it'll say to the learning part of itself, what do you think that is? And the learning part will come back and say, I think it's an A. And then you just say, actually, no, it's not. Bad. And like the learning part will say, what part did I get wrong? Oh, that part, I'll adjust that slightly. So that's where you adjust the inputs. So if we go back to here, you adjust the multiplications. It's how much you think that bit is important or how much you think that bit is important. That's why, like, when you're learning to juggle, for example, right? In the beginning, you might think, I've had this. I can juggle. I have juggled 5. I have juggled 6. I'm good at 3. I'm good at 4. Now, when you are learning to juggle, you think it's all about the catch. So you're trying to think like, well, I can catch this, I can catch that. The catch is important. But over time, you actually figure out it's not about the catch at all. It's all about the throw. You can be the best catcher in the world, but if you throw something and it's 5 feet behind you, you're not going to catch it. Juggling is all about throwing. It's all about throwing a ball so it lands in your hand when you want it to land there. And it takes a lot of training, that's the important word, a lot of training to figure that out. You might not figure it out in the actual words. You might not consciously think this is all about the throw, but your body figures it out. This is all about the throw. Now, when we're talking about recognizing letters, if you create a network, now in this case, when we're talking about the simple case where we're learning to balance a stick, it's just learning like velocity and angle, and then you can say if you go faster or slower, well then we'll learn to balance the stick. Learning to recognize a letter is a lot harder, because with a letter you've got it's a lot more complex. So it's not just a matter of zeros and ones and where are they. It's actually a matter of what do they represent. So what if it's rotated slightly? Or what if it's off to the left a bit? Is it still an A? Is it still a B? You know, for example, what is that? Is it an I or is it an L? You know? So actually I would call that maybe an I, because it's kind of short compared to this, you know, relative to this. Now what does relative mean? Well, to a robot, it would have to learn relative. Now, that I would call an L. But going back to this again, that I would call an I. So, but why? Why are we recognizing that as an I? Or why is it an L? Depends on the context. Yes, it depends on the context. That's where the relative part comes in. So if you've got something next to that, but context, again, is meta. It comes after the information. So you have the raw information, and the raw information gets parsed by a hidden layer into another hidden series of metadata. And the metadata might include information such as, that is a rectangle, that is or is a rectangle up there, there's a bright part here, there's another big part over there, or these parts are the same size. And then that gets passed forward, until out the other end you might get a letter, a word, a color, a cat, depending on what you're training. So it the information gets parsed, blah blah blah, until it comes out. That's how eyesight works. With eyesight, you get your raw information, which is the rods of your eye. So you've got 4 different kinds of rods in your eye. You've got red, green, blue, and you've got light. So it can determine whether something is bright or dark. 4 kinds for every kind of pixel of your eyesight. Now it's not rectangular. It's not rectangular. It's more like a sunflower shape. Like, if you think of it, it's just kind of, you can see something that's right in front of you, but you can also see things that are on the side, but not as much. That's because there are more rods in the center of your eye than there are on the edge. But it all eventually goes right back and forms an image where you're thinking of it as kind of rectangular. So how does that come out of something which isn't rectangular? Your eye is actually doing that for you. Scribbling notes down. Sorry. There's so much to know. All right. To do with the eye as well, there's these little movements called saccades, which are very hard to notice, but your eye is actually jiggling leftwards, left and right all the time. So what you're never actually looking very, very straight at something. And here's a really, really cool thing. If you were to hold your eye very, very still, all right, like hold your eye still, like on the eye itself, and just look at something and be very, very careful just to stare at that one thing. After 15 to 20 seconds, you won't be able to see anything. You won't see a single thing. It's not that your eye isn't working anymore. It's that your eye actually works by measuring the difference between the different things around it. That's why we have these saccade movements. So your eye is actually measuring values based on what it sees around you, and that's why you can see in the dark and you can see in the light, is because the different relative values are what you're actually seeing. You're seeing the relative values, not the absolute values. You can't see absolute values. So that's another thing, going back to Plato's ideals. When you're looking at something and you're saying it's red, like that's red, but is it really? Look at it at night. You might say, well, it's the same color. And look at it in the bright daylight. It might be the same color. You look at it and you say it's the same color. It's not the same color. If you take a photograph with a camera and measure the pixels, you'll see they are not the same color. They are red-ish, but they're not the same color. But your eye makes it the same color because it's looking at the relative differences between things. It just happens to yeah. Okay, so it's looking at the relative differences between these things. Now, when you're seeing this as red, you're not seeing the absolute value. You're seeing that basically your eye has determined there's a relative difference that makes it look kind of red, and I'm going to treat that as red. And it sends that information further back into the brain, and then that part might see rectangles and squares and shapes and stuff like that, and it will come back and it'll eventually say, I see a laptop. Now, what you see is just the laptop. You don't see the colors. You don't see the shapes. You just see what your eye network has eventually told your brain. Believe it or not, there's practically no information that's sent back. Hardly anything at all is sent back. I mean, if you think of the amount of pixels of information, I don't know how many rods and cones are in the eye, I don't know. But you don't see it all. You only see basically what your brain has determined as being important. You don't see the unimportant bits. Okay, it's 13:29. We don't have time. We don't have time to actually build the neural network. So maybe we'll do that for the next class, if anyone is interested. What do you think about that? Would you be blind permanently if you did this? No, you would not. ahead and try it. But if you focus in on the color of your laptop, your brain will tell you it is black. Actually, no, it wouldn't. If you think about this, right? Let's say you get a sheet of black paper. Okay, like you see your entire room and you have a sheet of black paper, and you look at this sheet and you say that is black. Okay, that's black. Now put that sheet up in front of your face so it is pretty much all that you see. Now tell me that it's black, because you're actually looking around it and you're saying, well, actually, like, there's a little bit of gray here. Oh, there's a small bit of fiber over here that I can see, you know, and this is not black. It's kind of a dark gray, you know, but you can see different parts that are different colors. When you put it down on the laptop, yes, it's black, because you're seeing it basically in relation to everything else, and your brain is saying, well, this is important, that's important, that's important, that's important. That's the black sheet. But then you look at it and you're saying, well, that part over there is a little bit darker than this. You can see that some parts are different shades. I'm like, when I'm saying like you don't see it, like you don't see the same colors, I don't mean that red gets mixed up with green. I mean that the red is a different shade. You know, like in the daytime and the nighttime, relative to everything else, you're looking at and you're saying it's the same shade. But that's because of the context. In the context that you're familiar with, you know that this red should be this much relatively more red than the other red next to you, you know? So you are basically seeing it as the same shade, even though in absolute terms it's a different shade. All right, brown actually is not a color. That's true. Okay, now I'll just explain why brown is not a color. Okay, there are actually only 3 colors that you can see. You can only see green, red, and blue. Every other so-called color that you see, like yellow, or white, or black, or pink, or anything like that, they're actually combinations of red, green, and blue that your brain has determined to be a color. They've just decided this is a color, this is a way of telling this apart from that. So brown is actually a combination of the 3 colors. Now, if you look at a rainbow, for example, a rainbow is actually it's kind of a pure ladder between infrared and ultraviolet. But if you look along the entire rainbow, you will not find brown in there. And that's because brown is actually a combination of the 3 colors, red, green, and blue. Okay, from red, infrared, green, which is in the middle, and then blue, which is all down the right. Now, there's another color which is not in the rainbow, which is purple. Purple is a combination between red and blue. Now, you might think violet. Violet is definitely there. Violet is not purple. Violet is actually beyond blue. It's where it's starting to get invisible to you. But purple is a combination between red and blue. If you think of it like that, it should be kind of in the middle, but green is there. Green is but green is a definite, it's a definite value. You can say that green, I can't remember what the actual wave value of it is. I think it's 330 nanometers. Yeah, so green is 330 nanometers in wavelength. How did I know that? I don't know, lasers. Black is the absence of all color. Yes, that is true, but that doesn't make it a color. All colors combined make white light. Yes, that's true as well, but that doesn't make white a color. It depends on, it depends on what you mean by color, the word color. There are only 3 pure colors that your brain can actually see, and every other so-called color that you see is actually a combination of those 3 colors. Okay. If anyone moves, they die. What about purple? Yeah, purple isn't the real color either. It's a combination between red and blue. and it's not in the rainbow. Basically, if it's not in the rainbow, it's not a real color ish. All the colors combined make white only at the same exact amount. No. See, at some point your brain basically just can't take more information. So white is basically, I have all the I have so much information that I cannot take any more. You could say that that's basically like, if you like, red is a certain value, but if you just put in more and more and more and more and more until your brain is basically exploding with information, you could say that that's white. It's become so red that it's like a piece of metal that's getting hot. Okay, this is not a pure example, but if a piece of metal, as it gets hot, iron, when it gets hot, turns red. The reason it turns red is because it's actually throwing out photons at certain the photons have a certain value which look red to us, but as it gets hotter and hotter and hotter, it turns white. Why do we not see the red anymore? Why? I mean, the same photons are still coming off, but there's more of them, and it comes out in higher values as well. If you put enough blue into something, you get white. Yeah. Anyway, all right. Has anyone got any questions about neural networks other than colors and philosophy and stuff? Ink, yeah. Actually, there's an interesting thing about colors, that you've got subtractive and additive colors. So, I like the subtractive ones are basically where you shine the light on it and it absorbs a certain color, and additive is where it actually gives out that color. So aliens might see different colors. Yes, actually, every single life form on the Earth can see in different ranges. So an example, an extreme example, is the mantis shrimp. And the mantis shrimps are incredible animals. They can do incredible things, but they've got 28 different types of light of color cone in their eyes. So that's, I don't know how many colors they can see, but you know, it would make making a TV very difficult that a mantis can see, you know, a mantis shrimp. The screens that you have in front of you, if you look very, very close at your screen with a magnifying glass, then you will see the dots of red, green, blue, and white. Okay, there are basically 4 dots per pixel: red, green, blue, and white. And each one gets a different value depending on what's going to be shown to you. Because every animal sees different color ranges, that means that what you see on your screen is not the same as what your cat sees or what your dog sees. So your dog might be looking at something and saying, well, why is everything blue? Well, your dog actually mostly sees in 2 or 3 colors anyway, so everything is kind of brownish green to a dog anyway. But your cat might see different colors and say, like, well, why is he looking at this thing? Why can't they make better technology? These guys are terrible. A mantis shrimp looks at it and sees, like, you know, stick figures. Useless people. They can only draw in black and white. It's terrible. So some animals can see different colors. Yeah. Can a neural net learn how to do philosophy? Yes. In fact, there are logic systems that basically you give it questions and it tries to figure out from the available information to it what are the correct answers. And there's a kind of machine logic called Bayesian learning. And because going back to the brain in the vat thing and Descartes, we can't know for sure that anything is true. So if I say to you, for example, that Donald Trump's a bit of an idiot, the information goes into your brain. Is it true? I don't know. Does Donald Trump even exist? I don't know. So all we can do is go based on our available information and based on, is the source of information trusty? So Bayesian networks are what's used in order to define for yourself whether something can be trusted or not. So you might, for example, trust what a teacher says because up until now the teacher mostly tells the truth. When they say something, it's usually right. So if the teacher was to say, oh, you can't go outdoors these days because the sun is too hot and it will kill you, part of you is thinking, well, I don't believe it, but another part is saying, but they've always been right before. Maybe I should listen to them at something about that. So that's how Bayesian networks work. Now, spam filters actually work exactly the same way. There's a friend of mine actually wrote one of the original spam filters called Spam Assassin, and it works based on Bayesian networks, where you train it. You basically say this kind of stuff is not to be trusted, this kind of stuff is to be trusted, and it's called ham and spam. Spam is the thing you don't want, ham is the thing you do want. I don't know what the vegetarian version of that would be, veggie ham. But anyway, so it tries to determine, it tries to say, well, what is it about spam that makes it spam? What is it about ham that makes it ham? So it tries to combine things and figure out, well, this makes it better, this makes it worse. And in a way, it's doing what neural networks are doing. And your Harry Potter and the portrait of what looks like a large pile of ash, that works the same way. So with Bayesian networks, there's a thing called chains. I think it's called Bayesian chains. Let me just check on that. No, it's called the Markov chain. But the Markov chain works off basically the same way that a Bayesian network works. So a Markov chain is where you take a certain number of words, and you can actually, there's a Markov chain probably in front of you in your phone. When you start typing something and it tells you what I think is the next word, that's a Markov chain. So a Markov chain basically looks at a series of words and it tries to predict what will the next word be by looking at examples of everything that you have ever written before. And if you do that and you just let it keep going and going and going, then eventually it writes a book. But that's exactly how those things work. So it's basically that you give it everything you've ever written, and based on that, if you write a word, then it can kind of guess, this is what I think you're going to write next. Now, it can be a bit smarter than that. For example, if you were to write a word that you've never written before, how is it going to figure out what you're going to write next? In that case, it will look back over everything you've ever written, and it tries to break it down into what they are. Are they verbs? Are they adverbs? Are they nouns? And it tries to determine, if you write a verb, what do you generally follow it with? And it will try and give you some information like that. Yes. I was trying to figure out what Bowen is saying there, but I think she's using the Markov chains to generate something. But you see, it looks so realistic. And that's basically how they work. It's you look at the last load of words that you've ever written and combine them into what are called n-grams. Now, an n-gram is a combination of words. And if you use that combination of words, then you can usually predict what is it that comes after that combination. It's not always 100%, so it'll give you a number of choices, like 50% of the time you write this, 25% of the time you write that. But if you always choose the highest value, well, then you'll end up with something that looks fairly realistic. Any other questions? Let me just go back over here. The AI that generates inspirational quotes, yeah. If I look very close at my screen, it just looks blurry. Use a magnifying glass or a microscope. In fact, you might even be able to use your phone. Let me just try this. I'm going to use my phone here and just take a photograph really close up of the screen and show you what it comes up with, if I can. So I'll zoom in, see if I can get it to. I can't seem to zoom close enough. Oh, there we are. Now, Let's look at that. So, lots of little squares, and you probably can't see it, but every single one of those squares is actually made of 4 different squares. And the 4 different squares are colors: red, green, blue, and white. You could take a photograph through a magnifying glass as well, and that would probably get you an even bigger picture. I have magnifying glasses, but they're attached to things, so I can't do that. Anyway, so that's an example. Right, where are my questions? I hope this was useful anyway. We talked about neural networks, and we talked about how they work. Now, I think in the next class, we'll take what we built of our robot, that little robot which is missing, and we're going to actually make it start thinking about what it's doing. So we'll start off by adding a little bit of a tilt to the stick so it starts falling. And then we can try and tell the robot how to fix it. So it'll train itself. Do you think creating a powerful and intelligent AI network is dangerous and ethical? That's, alright, there are pluses and minuses to this. The thing is, you have to give it examples of what is ethical. Now, people have tried this, where they will train a very large network on for example, law. So you basically, like, you give somebody a load of criminal cases, and it has to decide what. You give it a new criminal case, and it has to decide whether the person is guilty. But it has to be based on all previous laws and all previous cases. So if you were to take a robot and you train it with that information, then you find that it looks at things like, what is the color of the person? What is the color of the person that committed the crime? You know? Because all of human history is biased. And therefore, if you're training on that biased information, you're going to end up with biased output information. So you need to actually clean the information beforehand. And that's going to be very difficult because there's a load of information there. You have to go through and clean the information and train the AI on what is truly unbiased information. Even then, it's not unbiased, because what we think of as unbiased today is probably barbaric. You know, in 150 years, somebody's going to look back on us and think like, how could they do that? You know? I mean, if we think of like the early 19th century, for example, the early 20th century, Jesus, it's not even that long ago. Half the stuff of the 1960s or 1970s, you can't even show on TV. You can't show it on TV because it's so racist. There's a load of comedies, UK comedies from the 1960s and 70s that are racist, homophobic, sexist, and you could not bring them out today. Like, for example, the Carry On series of comedies. There's a series of films called Carry On whatever, Carry On Camping, Carry On whatever. They're soft-core porn, basically, okay? But they're very soft, but they're sexist, they're racist, they are homophobic, and, you know, you could not bring them out today. Because what we think of as decent today is nowhere near what was decent in the 70s. Because people change. So that's, going back to philosophy, that's why the Bible is wrong. The Bible says, like, a lot of people say what the Bible says is good, always. No, dashing a baby's head against a rock is never good. I don't care what the Bible says. Okay? Maybe people thought it was good, because what does good mean? Good means doing whatever God says. No. But what is good? Good is very hard to determine, you know? Like some people say that good is whatever improves the lot of most people. Okay, I think it's Stuart Mill, for example, an English philosopher. I think that was his thing was that that good is whatever brings happiness, increases happiness for the most people. But does that mean that you should be allowed to torture one person every year if it makes a lot of people happy? You know, is that good? It's very hard to determine what is good. Good is subjective. There's a series of philosophical problems called the trolley problem, and I really, really think you should look into that. Okay, another question. Let's see. So do I think determining a powerful and intelligent, right, going back to Alistair's question there, do you think creating a powerful and intelligent AI network is dangerous / ethical? I've handled ethical, right? Ethical, no, I haven't handled either, right? I don't even know if it's possible. It is possible to create an AI like that. Okay. Is it possible to train the AI to be ethical? No. I mean, yes, in a way, it's possible to train it to be as ethical as a human. But humans are not ethical. You know, what is good? I mean, we ourselves might say it is bad to be racist. And yet we ourselves are racist. Okay? No matter what we think, we are racist. You know, you might think like, oh, I'm not racist. Yes you are. Everyone is a racist, to some degree. You might consciously try not to be, but everyone is a racist. And it bleeds through. It comes out. It always comes out. Okay? I think the most important thing that you can do in order to try to be good, whatever that word means, is to try not let a lot of it bleed through. Okay? Try to be the same with one person as you are with another. Try not to treat one person better than another. Try to treat everyone as bad as you treat everyone else, if you want. If that's the way you do it. Like if you're a misanthropist, right? If you hate people, right? Hate everyone equally. If you like people, like everyone equally. It might not be possible internally for you to like everyone equally, but you have to put a face on it. You have to put an outward face, because the more good you put out, the more is reflected back. Right, next question. I was thinking more like Skynet. Yes. That's going back to the same question. Okay. The same question. Is a Skynet possible? In fact, a Skynet is possible from a completely ethical robot. Going back to Stuart Mill, I believe it was Stuart Mill, the idea that the best way to be good is to make the most people happy. What does most mean? I mean, if you got 7 billion people on the planet, if you were to force them to breed so there are 15 billion, and then you kill 4 billion, well, you're going to make a lot of people sad. That 4 billion, for example. But you now have 11 billion people which could possibly be happier. Is that a good thing? Well, according to a robot, it might be, because mathematically it makes sense to the robot. So it's kind of dangerous to assume that you know the answers to these questions. And I think that's where Asimov's books came in. Because Asimov wrote these rules for robotics, and the idea there was to come up with a foolproof series of laws that would make sure that robots cannot harm a human. And yet every single one of those laws had a flaw. And that's true in reality as well. All laws have workarounds or loopholes or whatever. Even like going back to the Bible, right? I was talking with this only a couple of days ago. There's a law in the Bible, in the 10 Commandments, there's one saying, thou shalt not murder. Okay? A lot of people say, thou shalt not kill, but that is not the correct translation for the word. Thou shalt not murder. What is murder? Murder doesn't mean killing. Murder means killing somebody when you're not allowed to kill them. So the law is basically, the commandment is basically saying, you're not allowed to kill somebody unless you're allowed to kill them. That's a useless commandment. Don't torture people. Yep. There is a very, very scary hypothesis. I don't know if, like, I can't remember the name of it. Don't care if a billion people get happy from the torture. From the torture of one tortured person, don't do it. Yes. Yes. It's very, again, that is actually the trolley problem, okay? I'm going to explain the trolley problem. Let's go back to this. Let's say you have a train or trolley or tram problem, the tram problem. Let's say the tram is following a line here, and at some point, let's say here, there is, gosh darn it. Alright, let's just put some vertical lines in here. This is fun. Okay, so I've just drawn some tram lines. Now, at this point here, the trolley can be diverted to one path or the other. Let's say there's one person here and there's 3 people. Let's say there's 0 people here. 0 people here and there's 3 people here. Is it ethical to divert the trolley so that it kills these 3 people? Okay? Now, the obvious answer is no. It is not ethical. You should not do that, because in this case, you don't kill anyone. In that case, you kill 3 people. Okay, let's go a bit further. Now we're getting naughty. Okay, is it ethical to divert to kill 3 people if by not diverting you kill 1 person? It still seems correct that you should not divert. The tram should continue in the same straight line and kill that 1 person. Now, just this is it's a hypothesis, all right? You don't have a way of stopping the tram. There's nothing. You can only choose one or the other. You must choose one or the other. Okay? Now, what if I tell you that these 3 people are murderers? And this person, as far as you know, is not a murderer. Now we're getting tricky. So now we end up with what you might call the calculus of ethics. Okay, so you need to now calculate how much is somebody's life actually worth. And that's, computers are very good at this, but humans are not. But it really is a choice now. Do you kill these 3 people or that 1 person? You only have one choice. Kill 3 murderers or kill 1 person that isn't a murderer. Okay, so that's... Now, a computer actually... It might look as if this is something that you might never actually need to think about. It's just a hypothesis, but it's not. It's actually seriously thought of today. And I'll give you an example. Elon Musk's Tesla cars can drive themselves. What happens if somebody is crossing the road in front of the Tesla and the Tesla has to make a choice between running that person down or going into a ditch and killing the occupants of the car? You know? So that's a serious question. Like, it only has 2 choices. Run the person down. We'll try to slow down, obviously, but you know that you're going so fast that you will kill the person. Or divert and go into a ditch. Let's say you're on a bridge. Divert and go off the bridge. So it's very difficult to do this, to figure out the maths of this, because you then have to think, like, what kind of person is it? Like, is it an old person? Is it a young person? How do you know, is it a murderer? Is it not a murderer? You wouldn't know this kind of thing. I participated in a survey for this, I think, for self-driving cars. Yeah. So they're basically asking people, but as we've explained already, people are biased. You can't trust people. Anyway, that's 2 hours. So I think in the next class we'll push on and actually build the artificial intelligence for moving the robot in this thing here, which we completely lost track of. So we'll leave it at that, okay? I hope you all enjoyed that. 1 minute left. 13:59. Tesla would never program their cars to divert and kill the driver. That would be asking for a lawsuit. Yes, but if Tesla allowed a car to drive over a person, that would also be a lawsuit. Cars shouldn't be going fast enough to kill somebody where they'll be crossing the road anyway. Yes, but what if somebody just climbs up off the side of a bridge and walks in front of you? Use that 1 minute to its full potential. I'm working on it. What is coding? Coding is language. So the more that you know about linguistics and how to speak to somebody, the more you know about coding. Coding is basically when you are telling a very, very stupid thing how to do something. And you have to tell it in such a way that it literally cannot misinterpret you. It's difficult. Car doesn't have to be perfect, just better than humans. Again, what is better? What does better mean? Philosophical. Alright, out of here. The answer is 42. Well done. Okay, I'll see you all later if I can figure out how to shut this thing off. Hold on. How do you turn this off? I keep forgetting this. End stream.